Morning. Okay, I just post the slide. So if you refresh on Blackboard, you should be able to find the slide. Okay, last class, we aimed at injective function. So we know that to show two functions are to show that a function is one-to-one or injective, we need to show that if you take any element from your input set, if their output are the same, that means their input need to be the same. Right? In other words, there's no two input goes to the same output. So this means no inputs have the same output. Okay, so we did two examples last time, right? We start with to show FA equals to FB and then end at A equals to B. Now let's look at this two example here. Okay, so is f of x equals to x cubed minus x squared an injective function? So again, to show this is injective function, we need to show for all A and B in the input set, which is the set of real number, we want to show if FA equals to FB, then we can imply A equals to B. So we will start with FA equals to FB, and then we will substitute it. Then we'll have A cubed minus A squared is equal to B cubed minus B squared. Then what can we do here? If you look at the left hand, so you have A cubed and A squared, right? So we can maybe take out A squared. So we can have A squared times A minus 1, and on the right hand side, we can have B squared times B minus 1. Now, can we conclude that A equals to B? Now, if you look at this, if I ask you what's f of 0 equals to? If you just look at x cubed minus x squared, we can write it as x squared times x minus 1. So f of 0 will give you 0. Now, what does f1 give you? Also 0. So what do we find here? We find that f of 0 equals to f of 1. So we have two output that's the same, but their input are different. Right, so we have two different input goes to the same output. So this is the counterexample, not injected. This function is not injective. So to show a function is not injective, you just give a counterexample, right? So find a outcome that's the same, but you have multiple input goes to that outcome. Any questions here? Now, if you look at the next function, we have set A, have the element A, B, C, D, and set B is E, F, G, H, and we have function going from A to B. Now with FA equals to E, FB equals to F, FC equals to G, FD equals to H. Is this an injective function? If we draw it out, we have A and B. We have A, B, C, D, and then E, F, G, H. A, FA goes to E, FB goes to F, FC goes to G, FD goes to H. Is this injective function? Anyone? Okay, so I see people say yes, it's injective. But if you look at here, every input goes to a different output, right? There's no two input goes to the same output. So this is an injective function. So let's look at two more. If we have f of x equal to x squared, is this an injective function? Okay, not injected. So if it's not injected, you need to give me a counterexample. Which you need to give me two input that goes to the same output. Okay, so you'll give me x equal to 1 and -1. So let's check f of 1. Then we have 1 squared is equal to 1. F of -1 give you -1 squared, and that also give you 1. So we have f of 1 equals to f of -1, but the input 1 is not equal to -1. So this is not injective. What about the next example? What about 2x minus 3? Okay, so I see people say it's injected. Now, if it's injected, then we need to show there's no two input have the same output. So if we have f of a equal to f of b, then we need to show a equal to b at the end. Then f of a in this case will be 2a minus 3, and f of b will be 2b minus 3. Right, then we can add 3 on both sides. Then we have 2a equals to 2b, and then we can subtract 2 on both sides, so we have a equals to b. Right, so we show that this is injective. Any question on injective function? Okay, then we will move on. Now let's look at the surjective function. So a function f from a to b is called onto or surjective function if and only if every element b in set b, which is the output set, there is an element a in the input set a with f of a equals to b. Then the function f is called surjective if it's onto. So what does it mean here? So this means here it should say a, here it should say b, and then there are some elements. So surjective function means every element in the output, there's an input goes to it. If you have more elements, right, it's possible that some of the output have multiple input goes to it. But when we look at surjective, we are focusing on the output. So surjective function mainly is checking, does every output have at least an input goes to it, have something that pointed to it. So we know this is a surjective function. But if there is any element that did not have an input goes to it, then it will no longer be an onto or surjective function. Okay, so the injective, we are focusing on the input, right? No two input can go to the same output. Where onto is we looking at the output, see is there an input goes to every output. Okay. Now let's look at the example here. So the first example, where we want to check if f is from positive real number to positive real number, and f of x is defined to be 1 over x, is this a surjective function? And we know that to show a function is surjective function, that means for all element in the output set, we want to find there exists a in the input set where f of a equals to b. So if we look at the first one, if we want to show, so we want to show for all b in the output set, there exists a in the input set where f of a equals to b. Now, if f of a equal to b, what does b equals to? Right? B will equal to f of a, where your f of a will just be 1 over a. Then you have your 1 over a equals to b. Then we need to find there exists a in the positive real number where f of a equals to b. Now, if your b equals 1 over x, then that means your a will equal to 1 over b. Or you take reciprocal on both sides. And we know 1 over b is a positive real number since you have 1 divided by a positive number. So you will also get a positive number. So this means for every b, you can find a, where the a will, you just let a equals to 1 over b. So you are able to find a, which is 1 over b, that's positive real number that will give you b. So you pretty much you solve for a. And then to check that your a is in the proper range, right? In the input set. Any questions here? Now I see people say, what if a equal to 0? If a equal to 0, then 1 over 0 is not a positive real number. But if we look at the b, we know b is a positive real number. I see people say, what if a equals to 0? The thing is your a cannot be 0 because 0 is not a positive number. And your a is an input, right? So when we define the function, we cannot let a in the input set. If the a is in the input set, this is not even a function. Then 0 have nowhere to go to. Okay. Now next, we have a equals to ABCD and b equals to ABCD. Now it's asking here, we have a and b, they both have element a, b, c, and d. And you have a goes to d, b goes to c, c goes to b, and d goes to d. Is this a surjective function? Okay, so people say no. And why not? A have no input. So since there is no input maps to A. Okay. Now, if you look at the first example of what we does, right, to show a function is surjective, then we need to show f of a equals to b, right? Then we will substitute f of a, right, to find what's f of a. And then since we want to check there will exist an input from the input set where f of a equals to b, then we need to solve for a, and then to check is the value belongs to the input set. Now solving the a from f of a it's kind of like looking for the inverse function. Right, so for those who maybe take pre-calc, I don't know, do they teach inverse function in algebra? Right, you know the inverse function is you solve for the input. Right, so if you have a function that y equal to something, then you will solve for the x. So if your function is a one-to-one function, from a to b, it's a one-to-one correspondent function, which means your function is injective and surjective, which, in other words, if your function is bijective, then the inverse function will be from b to a. So if your f function is going from f of a equals to b, then your inverse function will be f of b equals to a. Now here it says that your f is a function that assign an element from b belongs to b. So you assign an element b to a unique element in a. So your original function need to be injective and surjective in order to find the inverse function from set b to set a. Right, so if your original function have f of a equals to b, then in your inverse function, you have f of b equals to a. Okay, so let's look at an example here. So let's say for you know what, let's do the inverse function a little later. So let's look at this two more examples for surjective. Right, so if we want to show f of x equals to 3x plus 7 is surjective, that means we need to show there exists, like for all b in the output set, which is the set of real numbers, there exists a in the set of real number, right, the input set, where f of a equals to b. Then again, your f of a is equals to 3a plus 7. Now, if you want to look for a, your a, right, 3a will equal to b minus 7. Then your a will equal to b minus 7 over 3. And since b is a set of real number, then you have the set of real number minus 7 over 3 is also the set of real number. So for every element in your output set, there exists an element from the input set that goes to the output. Right, and also this is now like this is also the inverse function now. This is the inverse function from, we have FB equals to A, right? What's FB? F of B is equals to B minus 7 over 3. So this is your inverse function. But we will talk about this a little later, right? We are able to find the inverse functions also because this is an injective function. We show this is a bijective function. Okay, next. Okay, so here is asking, is f of x equals to x squared minus 13 a surjective function? Again, we want to show for all b in the set of real number, there exists a in this set of real number where f of a equals to b, and we have a squared minus 13 equals to b. Then a squared will equal to b plus 13. Then a will equal to plus minus square root of b plus 13. Now, can we say that square root of b plus 13 belongs to the set of real number for all real number b? Or is there a counterexample? Okay, so I see people asking what does the belongs to the set of real number means at the end for all the output. This means your number is belongs to, like your number is a real number. Right, so if you take all the elements from the set of real number, where this is your output set. So this is saying for every element you take from the output set, where our set is a real number, you need to find a real number input since your input is a real number. So you need to find a real number input where there exists an input that map to every output from the set of real number. So which we get down to this step. So this means if we want to get B as the output, then we need to let A equals to plus minus square root of B plus 13. So if this belongs to the input set, then we are able to find an input that map to B, which is this value. Now I see people say when B is less than negative 13. So let's check. So we have negative 14 is belongs to the set of real number, which is our output set. Then the A, to find the A need to equal to plus minus square root of negative 14 plus 13. And that will give you plus minus square root of negative 1, which is not a real number. So there's no input from set A, from the set of real number, that will give you an output of 14. So 14 have nothing mapped to it. So we know this is not surjective. Okay. And now we will move on. So we talk about, okay, CPO say, why do we choose 14? Okay, so we choose 14 because we want to find a counterexample. Okay, so we want to find an example where this is not a real number. And we know when we take a square root of something, we can't have square root of a negative number. So you will see it's impossible for you to have a negative number under the square root. So if you choose negative 14, you will get a negative number, which your a can no longer belongs to the real number. So this is not surjective. Again, to show a function is not injective or surjective, you need to provide a counterexample. So to show something is not surjective, you find an output that have no input goes to it. Okay, so we talk about injective and we talk about surjective. So we say if a function is one-to-one correspondent, in other words, bijective, if it's both one-to-one and onto. So one-to-one means injective and onto means surjective. So if your function is both injective and surjective, then your function is bijective, which you might also see as one-to-one correspondence. Where if you look at what we have earlier, but if your function is one-to-one correspondent from set A to set B, that means your function is bijective. So if your function is bijective, then the inverse function exists. Then the inverse function will just be from set B to set A, where f of B equals to A. So it's like you will take the original output as your input, and then it will return to you the input that will go to the output originally. So here should be like a -1 to denote the inverse function. So we will use the little -1 on the exponent to denote the inverse. Okay, so now here we want to determine the set of real number to the set of real number defined by f of x equals to 2x plus 4 is bijective. So we know to show something is bijective, we need to show it's one-to-one, which means we need to show it's injective. And we need to show it's onto, which we need to show is surjective. So to show it's one-to-one, then we need to show f of a equals to f of b, which we have 2a plus 4 equals to 2b plus 4. Okay, so subtract 4 on both sides, then you will get 2a equals to 2b. Then we divide that by 2 on both sides, we get a equals to b. So we show that this is injective function. To show a surjective function, that means for all b from the output set, we want to find there exists an a in the input set where f of a equals to b. And our f of a is equal to 2a plus 4 is equal to b. Then to solve for a, we have 2a. We subtract 4 on both sides, so we have 2a equals to b minus 4. And then we divide both sides by 2. We have a equals to b minus 4 over 2. And want to show for all b, for all real number b, there exists an a in the real number. So we need to show this a belongs to the set of real number for all real number a. So if you have a real number minus 4, it's still a real number. And a real number divided by 2 is still a real number. So we know this is true. So this is both injective and surjective. So this is true. F is bijective. Now, if F is bijective, then the inverse exists. Now, if inverse exists, that means there exists an inverse function from B to A, where if f of A equals to B, then f of B, f inverse of B will equal to A, right? So this is our inverse function. So this means f inverse B is our function. And if you look at it here, but we have A in terms of B. Okay, so we have f inverse of B equals to A, and we know A here is equal to B minus 4 over 2. So this is your inverse function. Now, if you want to write it in terms of x, then you can have f inverse of x equals to x minus 4 over 2. So first, you need to show your function is 1-to-1. Because if your function is not 1-to-1, when you take the inverse, there will be one input goes to multiple output. Now your function need to be surjective, because if your function is not surjective, when you take the inverse, there will be input that have no output. Okay, so if you're asking, if you put 1 for the surjective, what do you mean you put 1 for the surjective? For B is the output. Okay, if there's any question, try to send that to everyone so everyone in the class can see the question. Okay, so if you put 1 for the output, then your A will be 1 minus 4 over 2. 1 minus 4 over 2 will be negative 3 over 2, so it will be negative 1.5. Negative 1.5 is also a real number. Are we good here? So the inverse function, it's pretty much, so if you look at the f function from A to B, then you have your inputs at A and the inputs at B. Then the inverse function from B to A is like you are flipping the position of B and A. And then whatever here, right, this value now will point it to A. So you can imagine like you have a mirror image of your input and output set. So if your function is not injective, that means there are input goes to multiple output from A to B. Then when you take the inverse from B to A, oh wait, this is not a function. If your function is not injected, that means there are multiple input goes to the same output. Then when you take the inverse, then that means this B here or goes to multiple output, then this is not a function. Right, so that's why it need to be one-to-one, or it need to be injective. Now, if your function is not onto, it's not surjective, this means there exists some element in the outputs that have no input goes to it, like this. This is a surjective function. Then when you look at the inverse from B to A, then there will be some input that have nowhere to go, since there's no input goes to it originally. Then we take the inverse, there will be input have nowhere to go, then this is also not a function. So in order to look to find the inverse function, your original function need to be bijective. Now, if you're able to show your function is bijective, to find the inverse function, your inverse function is pretty much equal to the A you find from the work you're trying to prove your function is surjective. So you don't need to do it again, right? You can just put it in terms of X. Any questions here? Okay, now here is a summary of how to determine the different type of function. So we know about injective, surjective, and bijective. And bijective mainly just asking is your function both injective and surjective. Right? So if your function is both injective and surjective, then your function is bijective. If it fails to be one of the two, then it cannot be bijective. So if you are able to show they are injective and surjective, then it implies bijective. So let's look at how do we show a function is injective. So to show that a function is injective, you need to show that if f of x equals to f of y for arbitrary x and y from your input, then x and y are equal to each other. So if you take two output that's the same, that means that implies their input need to be the same. Now, to show that f is not injective, then you need to find a particular elements x and y where x is not equal to y, but f of x equal to f of y. So you need to find two input where the input are not the same, but their output are the same. So if you find multiple input that equals to the same output, then you show that your function is not injective. Now, to show something surjective, then you need to show for any arbitrary element in B, or for all element y in B, you are able to find an element from the input set A where f of x equals to y. So in general, you will solve for x and then to see if x belongs to the input set for every element in B. Now, to show something is not surjective, again, you just need to find a particular element from the output set where there's no input goes to that. There's no input from the input set that goes to that output. So to show they are not injective or to show it's not surjective, you provide a counterexample. like give a particular element from the input or the output set. Are we good here? Okay, then we will move on. Now let's look at this phi graph here. And let's call it graph A, B, C, D, E. Now I want you to tell me for each of the function here, are they functions? Are they injective function? Are they surjective function? And are they bijective function? I see people say there are 2E. Where do you see 2E? Oh, this is C. Okay, so let's look at the first function. Is a function? Is the mapping here a function?
Yes.
Yes. Now it's an injective function.
Yes.
It's a surjective function. No. So since it's not surjective, it cannot be bijective. Now, if you look at B, we know B, but every input goes to somewhere, so it's a function. But it's an injective function. No. A and D goes to the same output. So it's not injective, but it's a surjective. Yes. But if you look at every output that have an input goes to it. So since it's not injective, then it would not be bijective. Now, if you look at C, is C, okay, so we know C is a function. Now is C injective? Yes. Is it surjective? Yes. So since it's both injective and surjective, then it will be bijective. Now, if you look at D, is it a function? Yeah, every input have a arrow goes out. Now it's an injective. No, right? You have A and C both goes to the same output. So the answer is no. And it's a surjective. No. If you look at 4, have nothing goes to it. So if it's not injective nor surjective, there's no way it can be bijective. Now if you look at the last one, is E a function? No. But A here goes to different output. So this is not a function. If it's not a function, then it doesn't make sense to talk about it's the injective function, surjective function, bijective function. But you need to first to be a function in order to talk about are you injective, surjective, bijective. Okay. Okay, so this is what we got from the previous question. So we have function that's 1-to-1, but not onto but not 1-to-1, 1-to-1 and onto, neither 1-to-1 nor onto, and we have not a function. Now, if I ask you to compare the cardinality, what do we see? So if we have cardinality of A is less than cardinality of B, then what do we know? So that means we have something like this scenario. If we have cardinality of A less than cardinality of B, can we get bijective function? Which means that we have something like this scenario. We have less input than output. Can you form a bijective function from those input and output? No. Now, if we cannot form bijective, that means we must miss an injective or surjective. Which one are we missing? Which one are we not able to form? Surjective, right? So if your input set is less than, like strictly less than the output set, that means your function f of A going to B cannot be surjective, which is onto, right? But we also can say f of A must be 1-to-1. Because you can have all the elements, like for any function, you can just make all the elements map to the same output. It's still a function, but it's not 1-to-1. Right, so we can guarantee that it's an injective function when we when our input set is less than the output set. But we can guarantee that you cannot form a surjective function, because for surjective function you need to have enough input to map to each output. So if your input is less than the output, then you don't have enough input for the output, so it cannot be surjective function. Okay, so you can guarantee this, but you cannot guarantee that it's a one-to-one function. Okay. Now, if your input set, if your A is greater than output set, can we form a bijective function? So that will be the second scenario here. Can we form a bijective function here? Yes. How do we form a bijective function? Okay, I see people say by pointing an extra input to one of the any output. So if you look at, so that's pretty much this scenario. Right, you have A goes to 2, 2 goes to 1, C goes to 3, and then you have an actual input then goes to 2. But is this bijective? Bijective means it's both 1-to-1 and onto. But if you look at it, this is not 1-to-1. So can we form bijective function? Bijective function means it's 1-to-1 correspondent. That means every input mapped to a unique output, and every output have an input goes to it. So we cannot form a bijective. So if we cannot form bijective, that means it must fail to be injective or surjective. So if we have input element, it's more than the output element, what can we tell about the function? Well, now you have enough input for the output, right? Since you have more input than the output. So you definitely have enough input for each output. And besides that, you will have extra. So this means this must map to some output which already been taken. Which means it cannot be an injective function. It cannot be 1-to-1. Do we see that? So if your input set is greater than output set, you guarantee that you can form an injective function. Since you don't have, you have too many input. Right, so after each input uniquely goes to an output, you still have leftover input. So wherever the leftover one go, then you will have multiple input goes to the same output, which it fails to be the injective. But again, it does not guarantee that not being injective does not guarantee that it's a surjective, because again, you can have all the input goes to just one single output, and there will still be output that have no input goes to it. Okay. Now from here, what do we know? So so we know if. So if you just compare the cardinality, it will tell you what can your function be. But your function cannot be surjective or your function cannot be injective. But if you already know your function, if your function is injective, this implies you must have enough output for every input, since every input needs to go to a unique output. So if your function is injective, that means you need to have enough output for every input. So this means your output need to at least as large as your input set. Does that make sense? Because for injective, every input need to go to a unique output. They cannot go to the same output. So this means you need to have enough output for it. And this is actually a contrapositive of the first statement. But if you take not Q, which means your function let's see. It's actually a contrapositive of the second statement. So if you take the not Q here, right here you have your f of x cannot be the injective. So if we negate that, your f of x will be injective if, and we negate this. So your A cannot be greater than B, so it will be less than or equal to B. Right? And so if we take the contrapositive of the first statement, if your function A goes to B is surjective, surjective means every output have an input goes to it. So this means you need to have enough input. So your input need to be at least as large as the output set. Now, if your function is bijective, bijective means it need to be both injective and surjective. So you need your function need to satisfy that your input needs to be, your output need to be as large as the input, and also your input need to be as large as the output set, then it will force A to equal to B. Any questions here? Okay, so be careful of how we word those statements, right? Because the last three here, so if we know a function is injective, we can guarantee that this inequality is true. But if we know this inequality is true, we don't know, you can't guarantee that the function is injective. Because no matter what your input and output set be, you can always make it a function that's neither one-to-one nor homogeneous. Or you can always make this input and output set and not a function. So if you know, if you know about what's the input and output set, if you know about the cardinality, the best you can do is eliminate some of the cases, like here. If your A is less than, if your input set is less than the output set, or if your input set is greater than output set, you can say your function cannot be injective or it cannot be surjective. But you cannot guarantee that it's injective, surjective, or bijective. But if you know your function is injective, surjective, bijective, then you know the relation between the input and output set. So be aware of the ordering, right? Because we know P implies Q is not the same as Q implies P. So you can mess up the order. Any question here? Okay, if not, we will move on. Okay, so if we have two functions, right? Your f1 and f2 are functions both from A to the set of real number. Then we can add the two functions, we can multiply the two functions. But you need to be aware, right? We're only doing addition and subtraction from the set from with the function from set A. They both from set A, right? So the input set are the same, and then they both go to the output set R. So be aware of the input and output set. So if your both functions are going from the same set to the set of real number, then you are able to calculate the addition. Like you can add the two functions or you can multiply the two functions. Right, since they both from the same input set. Now, when you add the two functions, a real number plus a real number give you a real number. And a real number times a real number also give you a real number. So this just makes sure your results remain in the proper input and output set. Right, so if your both functions are from set A to the set of real number, then the result of sum of two functions or product of the two functions are also a function from set A to the set of real number. Right, so if you add the two functions, f1 plus f2 of x is the same as f of 1 plus f of 2. Same thing with the multiplication, f1 times f2 of x equals to f1 of x times f2 of x. So if we look at example, here are two functions, both from the set of real number to the set of real number. Then we have f1 plus f2 of x will equal to f1 of x plus f2 of x. Then this will just equal to x squared plus 2x plus 3. Then if we want to multiply the function, f1 times f2 of x will equal to f1 of x times f2 of x. And that will give you x squared times 2x plus 3. Now, if you distribute it, you'll get 2x cubed plus 3x squared. Any questions here? Okay. Now, if G is a function from set A to set B, and then we have F is a function from set B to set C, then we can compose the function F and G for all A in set A by we compose G to F, so we have F composed with G. Then we will have the function from A to C. So what it does is your F composed with G of A will equal to F of G of A. Right, so imagine you have So here we have three sets. We have set A, we have set B, and then we have set C. Now function G are mapping the element from A to B. Now function F take element from B to C. Now if we compose f of G, which will equal to f of G of the element, this means it will take the element from A, and then we will calculate G of X first. So we will take element from, A, and then calculate G of X first, which will take us to B, and then from there, we will calculate f of that number from B to C. So after we compose, you will take every element from set A to a final result of an element from set C. Again, let's so if you look at it right here is like a diagram, kind of as we just did earlier. So we have three sets A, B, and C. G will take element from A to B. F will take element from B to C. Right. So if you calculate G of A, that will take you to B, and then we will do F of G of A and take us to C. And this process, doing G of A first and then F of G of A to C, that is the composition of F and G. So if we look at an example, right, the same function, since they are both from the set of real number to the set of real number, then after we compose it, we still have function from. Since they both from R to R, and then R to R. So when we compose it, we will have a function from R to R. So F1 composed with F2 of X, this will equal to F of 1 of F of 2 of X. And we know we will substitute F of 2 in F of 1. Now F of 2 equals to 2X plus 3. Now we will substitute that into F1, which means wherever we have independent Z, we will replace it with X. So we have 2X plus 3 squared. So this will give you F1 composed with F2. Now, if we do F2 composed with F1, you will get a different answer. But you will have F1, or you have F2 here, and then you will put F1 inside of F2. Then you will substitute X1 into F2. So F1 is X squared. Now, wherever you see a X, you will substitute it with X squared. So you have 2 times X now becomes X squared plus 3, which will give you 2X squared plus 3. So do we see they are different? Any questions here? Okay, so we will finish the class here, and I will see everyone next week. Have a nice weekend.